Now I very briefly present you what is going to be discussed today. Let's see if I can share my screen. Back. Okay, so very briefly, the introduction to this webinar. The name is ConNetEU Cluster: Advancing Power Electronics in Distribution Networks. As a cluster between these two projects, we are going to go through the two initiatives, starting with the iPLUG. About power electronics and grid innovations. We're going to have the speech of Mark and Antonio, and then we will follow with Meptu Beza and Ahmet Yahya Parag as a closure. In the second part of the webinar, there is going to be the STAR presentation about solid-state transformer for high-voltage grids. We are going to have Eduardo starting, and then Angela with the dielectric fluid performance and storage system integration into MV grids by Maria. We will have an open Q&A session. As an indication for you, you can write the question in the dedicated section in the chat. We will go through all the questions at the end, so you can start writing, but we will take care of all the questions when we be over with the two presentations. And then we're going to have a wrap-up and conclusions by the two project coordinator, Oriol and Jonathan, that will sum up a little bit about what has been discussed before. So I will leave the stage immediately to Mark. I will stop sharing my screen so that you can proceed with your own presentation.
Yeah, hello. I think I need permission to share. Yeah, once you give me, I can do it. Yeah, thank you. So yeah, this first presentation, it's more about this planning operation for multiport converters and distribution systems. And here, myself and Antonio, we are going to present our contributions from iPLUG in this regard. And since this is the first presentation, I also want to do a kind of a review of what we understand as multiport converter, which kind of combines the concept of the two projects, I would say. So it's like a device that helps us to improve the flexibility, controllability, resiliency, and reliability for distribution grids and building applications. And the main things that we could do is helping to integrate more renewable generation, also interconnecting different electrical grids and equipment like batteries, EVs, or different type of loads. And we could add, for the case of grids, we could also provide grid services like the ones listed here. So for us, multiport converter is a kind of also improvement of what we usually call a soft open point, but with more number of terminals. And from our side here, what we have done in iPLUG is basically presenting a methodology to size this converter based on technical and economical indicators that I will explain later. Also, we have compared this solution with other traditional ones, like just connecting with a switch or adding the elements separated instead of all together. And yeah, in terms of operation, we have also checked how we can enhance the grid operation, like to avoid overloads or voltage variations, excessive voltage variations. And then we have been also developing like generalized average modelings for control and stability analysis with this kind of converters. And here it's a bit like the overview of the sizing methodology we have proposed. Basically, we take into account like demand profiles of different type of consumptions, also the profiles of different type of regeneration, especially for renewable generation. And then grid parameters, so in case we are representing the grid, that's important. In case we want to include batteries, also we need to characterize, we need as an input how we are parameterizing these batteries. And finally, some costs to make sure that this can be used later on for the decision, the final decision. And then here, depending on the methodology, we have these two first steps as optional. So since number of data we can have, it can be very wide for the sizing. Sometimes what we do is we just choose a specific number of representative days to ensure that we can all the sizing is computationally speaking short enough. And the storage sizing also, it's as optional part that depending on the problem we want to solve, we could have it or not. And the main core of the methodology, size methodology, is this one here that I'm showing. And basically here we do an optimization that has some objectives that typically go between trying to improve some technical indicators like maximizing renewable generation or minimizing power losses against some economical indicators like minimizing the cost of this of the multiport converter. And then we add several constraints, like for example the grid constraints or generation limits or battery limits, and based on that we apply all of this for the different days, and as a result we get like the characteristics of our storage system, battery system, the nominal powers of our multiport converter, and plus some additional information about generation, curtailment, or final cost of the batteries, and so on. And in terms of application, so we have two options. Basically, we either do an energy-based option where we simplify the grid, so everything connected to the multiport converter are subsystems energy, like energy nodes, where we interconnect like all the resources or components that we want to analyze. But in other cases, we also like to do more a bit detailed grid in order to consider like the overloads or the voltage variations. And just to give you a few examples of what we have done, we have used this approach for buildings. Especially this case study has been based on some information from one of the companies involved in the project called Infraestructuras. And the idea here was to see how different it is to integrate different elements into a building, if they're separated, like this is a scenario, or if we join them together with different multiport configurations. And we mainly see that this is scenario B. Again, the scenario A are the two ones that are mainly the most important. And also in terms of size, we see that the size of these converters are typically around tens of kilowatts. Then we have also used two use cases from a local distribution operator that we have here in Catalonia called ANEL. And the idea here is to analyze how this MPC can help to integrate renewables, other components, or also help to improve the grid operation. And in this case, yeah, it's basically we connect it like a soft open point, but adding additional terminals. And we see that the size of this terminal is very similar to the previous case for buildings, so around tens of kilowatts, kilovolt amperes or kilowatts is the size of this converter. And finally, for a medium voltage case study, here we want to specifically solve problem of minimizing the voltage variation especially, but we can also add other objectives like minimization of losses or the cost. And here we have done this as an example where increasing the load is where we see most of the problems, and what we could achieve basically was a decrease of 3%, around 3% of the voltage. And in this case, the converter that we're sizing, we are talking about few MVAs. So it's like 10 times more than the previous cases that between 10 and 100 times more than the previous cases I presented. So yeah, for this part, I will hand this over to my colleague, Antonio. So please, you can go ahead and I will move the slides.
Perfect. Thanks, Mark. So, as Mark mentioned in the previous slides, the multiport converter-based soft open points can be employed to improve grid operation. In these slides, you can see some examples of how this is possible. For example, a soft open point with multiple ports can lead to the reduction of curtailment from renewable energy sources, improve flexibility, enhance reliability of the grid, the fair reinforcement of the grid, or minimize losses and regulate voltage. In the iPLUG project, we mainly focused on loss minimization and voltage regulation. So, next slide, Mark. Thanks. Let's start with the voltage regulation, so minimizing voltage deviations. In the figure, you can see the IEEE 33 bus system that is a benchmark grid for distribution grid studies. And in this case, without distributed energy resources, we can observe undervoltage problems in the nodes at the end of the central feeders that are in red in the slide. So if you click now, we should see how we can use a multiport converter. Yeah, I think just next slide and the animation should be okay. Yes. So we can see how a multiport converter can be employed in order to solve this undervoltage problem. In this case, the soft open point has 3 ports. One is connected to distributed energy resources, and the other two to the feeders. Through this soft open point, we can schedule optimally the active and reactive power flows towards these feeders and solve the voltage problems that we observed in the initial system. On the right, you can see the voltage profiles for the different cases. When we have the multiport converter, we have a better case for the voltage profile. Similarly, we can modify these P and Q set points, so active and reactive power set points, in order to solve congestion. In this case, we have distributed energy resources in the grid, and we are assuming to have a congestion in the central feeder. So again, in this case, we can optimize the set points in the different ports of the multiport converter in order to solve this congestion. On the right, you can see how it is possible also to optimize the soft open point in such a way that the losses in the grid are minimized. For example, by reducing or minimizing the current flowing in the most resistive lines of the grid. From the graph on the right, we can also derive different insights. The first one is that the position of the multiport converter is crucial for its optimal operation. Indeed, some locations are better for minimizing losses. And the second one is that if we use the soft open point to minimize voltage deviation, we could have antagonistic effects in terms of losses. So let's take the example of the location 1822. In this case, the losses increase with respect to the case without multiport converter when we want to minimize voltage. So the operator should operate soft open points carefully based on their objective functions and knowing that this could affect other technical parameters of the grid. We did the same analysis with more than one multiport converter, and what we found out is that after the first soft open point and multiport converter in the grid, the benefits start to be incrementally lower. So the initial one gives a lot of improvement in terms, for example, of voltage deviation reduction or losses minimization. However, as we add more into the grid, of course, their benefit starts to decrease. Then, once the optimal active and reactive power set points are scheduled through the methodology that we developed in the iPLUG project, local controls should ensure that these set points are followed regardless of grid conditions. For this purpose, a generalized average model and its linearized version was developed in the project in such a way that the control strategies could be designed and tested. And the linearized model in particular was employed to carry out a small signal stability analysis. So an analysis of this grid-connected soft open point based on a triple active bridge to small deviations from the steady state. Here you can see an example of a sensitivity analysis that was carried out, in this case, for different inductance and resistance values of the grid, and for different oscillation modes, so lower or faster modes in terms of frequency. And that's all, and thanks for your attention. And we also have the deliverables available that describe all of this work.
Now?
Yes,
Yep.
it's okay now.
Yeah.
Thanks.
Okay. I will talk about medium voltage multiport converter design and control. So my highlights or the contents would be to give a background, which is already covered somehow, and I will give a highlight of how we review converter topology for this application and select something that's appropriate for the application we want to see, and we will demonstrate some laboratory verification for that. So if I talk about why multiport converter, I think Mark and Antonio covered it. We need converters anyway to interface a large amount of renewables, energy storage, and provide services to the grid and all of these functionalities. And why multiport? Because it provides a concise and integrated solution where we can create some flexibilities. So specifically for this work package, what I deal with is to revise available solutions and come up with a multiport converter solution that's suitable for medium voltage. So that will be the objective. And a number of things we see in this selection: reliability, complexity of design, and modularity, power density, efficiency, and all of these factors we will consider. So where do we start for this? The first thing to compare and look for solutions is to choose a case where we can apply this iPLUG, and we have a scenario where we want to interface two medium voltage AC grids like this. So we have the option that the voltage levels could be different, and we are also taking a case where we have to integrate PVs or energy storage at a level of 400 volt and 800 volts, which means we have medium voltage on the AC ports 1 and 2 and low voltage DC, and this has to be integrated together, and we have a number of solutions. And these solutions are in general can be classified where the ports are directly coupled and there is no isolation, or you could have isolation in all of the ports, or you could have a mixture of both. So we investigate all of this, and of course that takes a lot of time, and we try to screen appropriate topologies, and we make a final comparison, and we come up with a topology that we think is best suited for the application. The case being medium voltage, as a starting point, it comes down to the use of a series connection of units. So multi-level converter would be the converter topology we would have to use on the two AC ports. And depending on how we couple these ports, we will have either low voltage DC, high voltage DC, or an intermediate one that will decide the design, how to interconnect or interface the DC ports. So these are the driving factors that will decide which options we need to go for. So we look for literature to find the solutions. The starting point was to have an enhanced soft open point solution where we have a back-to-back connection, either a DC link in between or direct AC-AC connection with and without isolation, and a combination of them. And we include important factors like what is the voltage and current characteristics of our different ports, how is the modularity, how can the design be flexible if we work with different power level, different voltage level, how is the fault tolerance. All of these are taken into the evaluation, and we make a conclusion. So from all this, a little bit of a description, this is a typical back-to-back where half bridge some modules are used, where you will have a high DC link and you would have to realize a low DC volt with a DC-DC stage, non-isolated. And this is a common topology we were also investigating in the project, where the isolation stage or the interconnection between the ports is provided by high frequency transformer, or as we call it DC-DC stage, where the SSTAR partners will present later on. So we use that as part of the module. And the last one is to use the best knowledge, the experience, the reliability of the technology on the back-to-back using half bridges, but converting them into full bridge cells to take advantage of the flexibility we can get into the voltage level we generate on the AC side and on the DC side would be different. We can't do a lower DC voltage level, then where interfacing a low voltage DC would be much, much easier. So we made a qualitative evaluation of this topology, which we call it partially isolated, where the two AC ports are coupled, but the DC one is isolated. We need this to have different requirements on the low voltage DC and an intermediate DC, as well as to go from an intermediate DC voltage to get a lower DC voltage to get the voltage scaling. And this is the one where it's an AC-AC solution where we use high frequency DC-DC stage, where that is the one that transfers power between the ports, which you will be familiar with. So we make a comparison between these two, which option to be the most feasible one, where we screen this out because of the difficulty of realizing a low voltage DC from a high voltage DC. Because if we use half bridge cells, then the DC voltage and the AC voltage are coupled, we lose the flexibility, and we do this kind of screening to come up to a final topologies to choose from. So we have these two topologies, where one is like a normal back-to-back configuration where series connection of cells would realize the AC ports, and then we will have an isolation stage to go from an intermediate DC to a low voltage DC to realize the DC port. And this is typically the other one where you have a configuration like this. This is the high frequency DC-DC stage, where this provides a coupling, the power transfer between the AC ports, and also a connection point to realize the DC level. So by playing with the DC level of this topology, we have decided how to optimize or how to have a comparison solution between these two. And a partner from in the project does this analysis, and we come up with a conclusion like this. Qualitatively, we could say that if the voltage level, DC link voltage level can be reduced, the solution like the soft open point solution with a DC link, where the DC link is low and having an isolation between, is a solution we go for. And these are some key figures we could use to motivate why that solution. So we have analyzed or reviewed all the topologies. We come up with candidates of different configurations, and then we choose the one which will take the advantage of the available solutions, which is basically two AC ports coupled together with no isolation, and a low voltage DC port which uses an isolation stage, where the voltage reduction is done by having a series connection of the input side and a parallel connection on the low voltage DC side. So which means that this is the topology we go for, which means that if we use full bridge cells connected in series, so we can have different voltage levels in this port or in this port. The voltage level can be reduced to a value we want depending on the current level. And we have an isolation stage where this intermediate DC voltage is realized by a series connection of one side of the isolation stage, and the output side can be connected in parallel because this is a low voltage side. So this is the one we have, which means that we have the flexibility to provide or to connect two different AC voltage levels, where the DC voltage level can be used to optimize the number of components and the performance. And we can also easily integrate low voltage PV or energy storage or DC loads for that matter. So we have this one, and what we did was to evaluate this performance, the performance of this topology. And the first thing we did was to implement this one in simulation, and we make a lot of tests. Then we check that it works, which we will provide in a deliverable. But the main part, which is coming from Chalmers, is to build a low a downscaled version of this one in an actual lab and to make some tests. So for that, what resources do we have? We have a multi-level converter. We could realize one of the ports. We have a grid emulator to realize an AC voltage. And in this side, we have another converter. We use two level to generate a different voltage level, and we connect impedance loads. And on the DC side, because we are working on low voltage, and the motivation to have the isolation stage is not that important, and of course we don't have the resources as well, so we connect constant power load on this one, impedance load. But because the DC link voltage is controlled, we could say that this is a DC load connected to the DC port. So we have a 3 port. We interconnect different voltage levels, and we try to test this one, having a number of runs. In pictures, this is what we have: a 2-level converter to realize one of the ports, and this is a multi-level converter, an empiric system to interconnect the other side of the AC port. And this is a grid emulator, and then the DC side of these two converters are connected and it is controlled, which will be also the connection point to realize the DC port. So you could say that this is an enhanced soft open point, and this is a DC source where we could use it also as a DC load. Having this, we run a number of tests, and of course the number of tests we did are a lot. We do connection, sudden connection and disconnection of loads, grid faults, power steps, and a number of things. And I will demonstrate some of the results we got. All of them seem satisfactory. So the first step we did was to apply a load step on the DC port, and you could see that the DC current abruptly go up where the DC voltage is controlled. We could see that when we deal with multi-level converters, as you all know, that the most important factor to keep an eye is keeping the energy or the capacitor voltage to a decent level. The average capacitor voltage is like this, which means it always sees a low dynamics when there's a power transfer, but they are balanced, and it seems working. And we apply also, to create some abnormal conditions, we apply an unbalanced grid on using our grid emulator. So we could see that we inject unbalanced currents, which will also add 100 Hz oscillation in the power outputs. And the circulating currents are different, which would mean that the capacitor voltages are unbalanced, and this would not be an operation we want. So what we need to do here is that we have to provide a negative sequence controller, at least, to have a power exchange without the negative sequence, as well as we need to have a balancing scheme where the phase legs of the capacitor voltage should be controlled at a decent level. And then what we did was then to implement those, and we have done a balanced exchange, and then the capacitor voltages remain balanced. As you could see that the offset is not going up, the capacitor voltages, as you can see, are staying balanced. So showing that things work as we want. And of course, the next step would be, depending on the resources, of course, we have used a simplified version, and depending on the availability of the resources would be to upgrade that. We could use multi-level converters on the two AC ports and actually add also an isolation stage. But so far, this is what we have, and we will document this soon in a deliverable for the project. Thank you. That's what I have.
Thanks a lot for your speech. Okay, let's move forward to the last one, Ahmed, for the iPLUG. If you can share your screen.
Yes, I think I need to wait for Mepto first to stop sharing, and then I wait also for my access.
Okay.
Okay. So perfect. Now I have. So good afternoon, everyone. I am Ahmed Yahya. I am a postdoc researcher at University of Padua, and I'm going to present our research activities on low voltage multiport converters. So with a quick recap of our main objectives, so we are focusing on developing multiport converters in low voltage networks to attain higher efficiency, more compact size, and easier scalability compared to conventional multiple converter approach. And we tackle these low voltage networks in two scenarios. The first one is the residential level scenario, where we focus more on proposing novel topologies that attain better efficiency, improved power density, and reliable power conversion. And in this scenario, we are limited to a few kilowatts of the converter rating. So most of our studies and experimental verification limited to 10 to 20 kilowatt. For a higher power level at the distribution level scenario, we focus more on controlling the multiport converter to provide grid support and to have a fault right-through capability, and also to ensure passive impedance at all ports. And this, of course, a higher power scenario where we consider a few hundred kilowatts. So starting with the many challenges and motivations for the multiport converter, as we can see, our modern power system is experience a huge penetration of these systems, and the main challenge is to how to integrate these DC systems in an optimal way. because the current approach to have a separate converter for each DC source or DC load will result multiple conversion stages. We think it's not the optimal way, but using the multiport converter, we could potentially enhance the efficiency. We could attain a reduction in total cost size of the power electronic interface of the multiple ports, and we also attain additional flexibility by enabling direct power transferring among different ports. Another challenge related to the DC systems, anyone has some experience with the DC system, one of the well-known obstacles is the lack of voltage standards. So we have for low voltage DC systems a wide range starting from 5 or 12 volt to 1.5 kilovolt. This not only affecting the selection of the semiconductor devices and the passive elements only, but also affects the topology selection itself. So if you are going to interface the European low voltage AC grid with DC systems higher than 566 volt, you need a boost type or a voltage source converter. Or if you are going to interface with these systems lower than 490 volt, you need a buck type or current source converter. And towards standardization, there are some efforts that recommended the 400 volt DC systems as it's proven to attain optimized efficiency and cost, especially for residential level scenarios. So most of our studies will focus on 400 DC volt DC systems, but we also have the motivations for buck boost multiport converter to interface wide range of these systems. And finally, the challenge of the existing topologies of the multiport converter. One of the common approach to develop the multiport converter is to couple conventional converter to an intermediate DC link. This approach is we still have the multi-stage power conversion. We need a bulky intermediate capacitor, so we potentially decrease the efficiency and power density. We have also the approach of having a multi-winding high-frequency transformer, although this attains an isolation and potentially soft switching for most of the operating range, but we still need a bulky magnetic element that also is challenging to design, and potentially there is also a decrease in efficiency and power density. And the last approach is readopting some of the multi-level converters to operate as a multiport converter, like what is presented here. A 3-level inverter is used as a multiport converter, but usually this kind of topologies has a lot of limitations in terms of power flow and dependence on the voltage level. So that's why we propose novel topologies starting from a 2-port topology called the Y converter. It's interesting topology, has a lot of features like single stage power conversion, buck boost capability. The first topology we have proposed is called the multiport Y converter. So we extended the 2-port topology to have more interfaces with these systems. We still have very interesting features like single stage power conversion. We don't use any bulky components like multi-terminal transformers or intermediate DC link capacitors. We still have the buck boost capability by directional power flow at all ports. And with this way, we called a symmetric way to extend the topology to multiport. We use 6 switches and 3 inductors for each extra DC port. We also proposed a multiport converter in a symmetric way. So we only use 2 switches and single inductor to interface the extra DC port. And of course, this more interesting as it leads to a more simple and compact converter, but it's more convenient only if the additional port is at lower power. We have done a lot of detailed comparison to demonstrate the effectiveness of the multiport converter compared to the use of 2 separate converters. Here we evaluate the efficiency for the whole operating range if we have 2 DC ports operate at plus or minus 5 kilowatts. And as we can see from the loss map, we have lower losses. We can see it from the larger blue area in the case of the multiport converter, so we attain an improved efficiency for most of the operating range. We enable direct power flow between the DC ports through the topology itself, rather than circulating the power from one DC port to the AC grid and then to the other DC port. And we also decrease the number of the used semiconductor devices. We then move to a more systematic evaluation using Pareto and multi-objective optimization. So we have a real mission profile for PV and storage coupled to the EC grid. And as we can see from this figure also, the multiport converter attains improvement in both in both terms of efficiency and power density. So we are optimizing the power electronic interface between the DC systems and the EC grid. Then we have moved to the experimental verification. We developed a prototype based on Emberx silicon carbide modules and also some designed modules for the EC side. We design internally in our labs to have an improved features for these specific devices. And we tested in a lot of scenarios. I'm just showing some results at transient when one of the DC ports have a power step from 10% to full power, and also when one of the DC ports moved from working in as a load to fully working as a source, and now the DC ports are exchanging the power together without depending on the AC grid. So as you can see here, the AC grid current drops to 0, and now the DC ports exchanging the power together. We did also some efficiency evaluation. Of course, now as we are a 3-port converter, we need a 3D efficiency representation to show the whole spectrum of our converter. And even we are using a rapid prototyping approach, we attained efficiency almost at 96%. We have published a quite good number of publications in top journals and conferences. I'm putting here just for reference. And as a conclusion, as our modern power systems experience more these systems, we are optimizing the coupling between these DC systems and the existing EC grid. The main challenges are the standardization of this voltage level, the existing multiport converter topologies, and the higher number of integrated systems. That's why we propose the multiport converter and the asymmetric multiport converter. And we have also some other interesting research activities in the scope of this work package for low voltage multiport converters. We tackled also the fault rate through multiport converters, nonlinear control of 2-port and multiport converters, and also to ensure all-port impedance specificity. And you can find more information about this in our repository on Zenodo. It's called iPLUG EU, and this is the specific link for our first deliverable. So it summarizes almost all of our activities. And also I keep here my contact information in case of you would like to discuss more about this, or you need to start some collaboration. I would have to do so. Thank you.
Thanks, Ahmed. Thank you very much. So we have finished the first part related to iPLUG, and now we move on with the second project, that is STAR, and we start immediately with Eduardo.
Hi, everyone. I'm going to introduce a little bit the STAR project and also talk about the high isolation, the developments that Circe have been done, and it's working on in this project. Mainly focus on the design of the high isolation IPT for medium voltage cascade H bridge. So first, I'm going to be a brief introduction about the why in the modern grids with a high percentage of DC generation and loads. The integration in DC has a more efficient and cost profitable operation due to the reduction of different converters like the DC-AC installation. So for what? So for when we connect this DC grid, medium voltage DC grid with the AC grid, also with the medium voltage, we call it this element the solid state transformer, and this solid state transformer, it's fully controllable equipment with the possibility of control bidirectional power flow, and it allow us to integrate better the DC generation and loads like renewable energy, electric vehicle, or for example battery, and also improve the modularity of the grid. And the core of this solid state transformer is the medium frequency transformer that allow us to it's like a Lego piece that allow us to serialize the converters in order to reach a desired voltage, or parallelize it in order to reach a desired current. It is power. So this medium frequency transformer, that is the connection between these two DC-DC converters, allow us the possibility to go with power electronics to medium or high voltage, and also it has, as we have seen, thanks to our colleagues, it is possible to interconnect also AC-DC converters to interconnect with an AC grid working at different high levels and any frequency, and also in the other side, it's possible to connect to another AC grid. So the scheme of the solid state transformer that are focusing on this STAR project, we have create this solid state transformer for 72 kilovolts of medium voltage grid. So we have performed two developments in the side of this project. One development is the control of a decentralized cascade edge bridge control. There is a grid following converter for medium voltage grid. And the second development inside of this project, that is one it is focusing today, is the DC-DC converter at working at 75 kilowatts with 72 kilovolts of isolation. So this converter that we already develop, it's a converter that is bidirectional with a bus voltage of 1.5 kilovolts, and it is working with a resonant tank that will be operated at 50 kilohertz. And the main one of the main goals and issues and the problems that this kind of DC-DC converter for medium and high voltage application is the isolation that is needed from the primary side to the secondary side. So in this project, we have developed, based on an old patent, this medium frequency transformer based on an inductive power transfer system. That allow us to have a connection between these converters with based on this inductive power transfer that allow us to connect it, giving the isolation, requiring simplifying it, because we can, for example, we can increase the gap between the primary and the secondary in order to reach the desired isolation, but due to the design, we can reach also high efficiency and high isolation capacities. So this design has been shown in our last research paper that we have sent it the last months, and it's based on this this medium frequency transformer designed by this inductive power transfer system. That is, as we can see here, double D design with a high voltage isolation between primary and secondary, thanks to this split planar transformer, and it is as an isolation between primary and secondary. It is oil filled with a dielectric fluid developed by Novamont, that after me is going to talk about this development. Thanks that this design, it has a better heat extraction, thanks that we can remove the heat of the coils and also of the magnetic elements at every side of the IPT, keeping the isolation in the middle in this oil. Also, we minimize the electromagnetic interference thanks to this double D configuration, with a reliable performance with low magnetic parameter deviation, thanks that it can be very replicable, these designs, because we can, thanks to the drilling machine, I mean, for it is easy to build this kind of planar transformer without low deviation of in the manufacturing process. So all of them, all the design has been automated using FEM software, and it has been done simulation in 3D in order to confirm all the results. I have to say that this double D allow us to reduce the losses, thanks that all the magnetic or most of the magnetic field, it's interconnected between these two IPTs, and low of them is going to the enclosure, reducing the total losses and increasing the efficiency. So we are now in the testing phase, and this IPT has been designed by Circe, but also manufactured by our partner, our colleagues from EFACEC from Portugal. So that's all. I leave the floor to Angela for.
Yeah, hi everybody. I am waiting for the permission to share.
Can you see it?
Okay, here it is.
Okay.
Okay.
Let me see.
I am speaking on behalf of Novamont today, and we will share some insights on the job that Novamont has done on the development of biodegradable and renewable dielectric fluids. But before navigating the topic of the present presentation, I would like to share a little insight of who is Novamont and what are our activities. So next slide. Of sustainable biopolymers and biochemicals. We was born as on the legacy of the school of the Montediso schools of material science, and we have been recently acquired by Versalis ENI, which boosted further the development on about circular economy. Next slide, please. So bioeconomy model of Novamont is rooted on three main pillars. The first one is regeneration of dismissed industrial sites. That means that we transform disguised or non-competitive industrial areas in new competitive areas focused on biorefinery projects. The other one is developing agricultural supply chain which are based on low input crops with that preserve soil and even restore it. And then the philosophy behind the production of our product range lies in the effort to not only create products but creating solutions for solution to the pollution of soil, air, and water. So point is not only worry about the final product, but also the entire life cycle. So the sustainability in the production, during use, and then in the end life. As I said, Novamont. Next slide, please. As I said, Novamont try to leverage the exploitation of biodegradable materials. So we have a production of biomasses which are transformed with two main processes: a chemical process and a biotechnological process. Among different products, we have developed a strong know-how on vegetable oils and a strong know-how on the synthesis and formulation of biodegradable synthetic esters. And inside this framework, we have developed the products that we are testing on in STAR projects. Next slide, please. Our effort in STAR project, in fact, has been devoted on the production of biodegradable fluids, which are actually a very important, let me say, tool in the good functioning of the entire equipment. In fact, insulating fluid must ensure that certain performances of insulation must be maintained, and also that using the right dielectric fluid ensure also a safer use of the SST modules. So one in the work package of held by Novamont, we focused on developing this biodegradable dielectric fluid, but also in ensuring, with the cooperation of RINA, all the health and safety assessment related to the biodegradable dielectric fluids, and with the cooperation of CERT, we also focused in establishing which would have been the inception of a breakdown voltage scenarios during the use of these biodegradable fluids. So next slide, please. So the final effort of our activity on this project has been focused on in supplying a certain amount of biodegradable vegetable-based electric fluid to CIRSE and EFASEC partners. But the reason why we focused on biodegradable electric fluids is because, of course, when talking about transitioning towards smart grid and the use of solid state transformer, the only solution can be also to evolve in fluids with a better performance and a better environmental profile. Next slide, please. So these fluids, when compared to mineral oil-based fluid, can ensure two properties. The first one is the rapid biodegradability that minimizes the environmental impact in case of accidental spillage. And the other one is that all the production of this oil can be more sustainable, because we are they are based on renewable sources, and they are manufactured with a more eco-friendly manufacturing process. And then there can be also an effective end-of-life management. Next slide, please. So the three pillars for the main that make this oil a better choice for, especially for the newest assets regarding the production of energy, are safety, because these oils have a flash point which is way higher. That assures that this kind of oil lower and minimize the risk of ignition and propagation of fires. The other one, as I said, is the environmental advantages of this oil, such as biodegradability and low toxicity, also for operators in case of accidental spillage. And then also there is a technical aspect, which is the protection equipment, the protection of the equipment. We assessed during the whole work done within the SSTAR that these oils could be compatible with the materials used to build up the SST modules. In general, these kind of oils are able to better protect the parts of these equipments, such as craft paper, wood inside the equipment, and are protective towards also metal materials. Next slide, please. So during the project, we basically worked in order to formulate two kind of products, which are an ester-based dielectric fluid and a vegetable-based dielectric fluid. Then we selected for the scale-up the vegetable-based dielectric fluid because it showed as the most promising of the two fluids. And these fluids were supplied to Circe. The fluid complied all the project specific technical requirements, such as the compatibility with the materials and the being in line with the ISC standards. Next slide, please. So if we talk about the development of more sustainable grids and system with more resilient transformer, we should consider also the development of this kind of products, which allows not only a more sustainable functioning of these grids from an environmental point of view, but also from a safer functioning of these grids from a technical point of view, due, for example, to the higher flash point and the better protection of the equipment. Thank you.
Thank you, Angela. Okay, we manage. Maria, do you want to share your screen?
Yes, of course. Hello, everyone. Am I the last presentation for today? I think I am.
Yes, you are.
Okay. Let me try to share my screen first. Tell me if you can see a PowerPoint presentation in presentation mode.
We do.
Oh, perfect. Okay, I'm good. Well, before I start, I would like to say it is really interesting that we have gathered so many people from totally different backgrounds today. I myself do mostly energy management, day-ahead optimization, quite different than what has already been presented. So my presentation is kind of different as well. And I have kept it kind of simple because it is the last one and I didn't want to, something light for the finish. If I change the slides like this, do you see it?
Yes. Yes, Maria.
Oh,
Yes.
okay, perfect. So let's begin. First of all, my name is Maria Fotopoulou. Nice to meet you. And I'm an electrical engineer at the Center for Research and Technology, Hellas, which is CERT in Greece. And I'm here today to present this presentation about storage system integration into medium voltage grids. Well, to begin with, about storage systems, there are several types of technologies. The main storage types are electrochemical, such as batteries and supercapacitors and fuel cells. Then we have the mechanical types, like hydropump storage, flywheel, compressed air, and so on. And of course, we have the thermal energy storage. Now, in medium voltage, the most adopted storage types are the batteries and then the hydropump storage systems. And so far, the main application, let me close this window. So far, the main application of medium voltage storage is the non-interconnected islands because there is no support or connection whatsoever with the mainland, with the main power system. So for example, here you can see the medium voltage hydropump storage system of Ikaria, which is an interconnected Greek island comprising 3 reservoirs and 2 hydropower plants. And here you can see medium voltage and low voltage storage combinations in the interconnected islands of Terceira, Madeira, and Porto Santo, comprising fuel cells, hydropump storage, batteries, V2G, flywheels, and so on. And here I have also included this table to make it even more apparent how important the medium voltage storage system is with other non-interconnected islands in Europe, like the Faroe Islands, like Agios Evstratios, El Hierro, which has a really interesting hydropump storage system, and so on. Now, these were the past applications, but in the modern power systems, we have a few, a few innovations, a few challenges, a few shifts. So let's check the current and future prospects. The most promising one is the energy community. So in energy communities, we have the shift from energy metering to net from net metering to net billing policies. This means that the medium voltage photovoltaics alone are not adequate for the energy communities. The medium voltage storage system is required. So the question is how to size this medium voltage storage system, how to connect it, and how to operate it. So in this case, the solid state transformer, the SST, is key for the proper energy community operation. And for this purpose, the STAR project has informed and interviewed Ms. Miriam Rodriguez-Ruiz, who is the president of Electra Energy. This is an organization supporting all Greek energy communities, and you can see in this figure how many of them are. So this is a market, a potential future market for the solid state transformer. Now, apart from energy communities, we also have microgrids. So we have distributed resources in the modern power system, like renewables and storage systems. Of course, these have advanced control requirements for power quality and stability. And here the question is how to regulate voltage and frequency and how to manage all of these resources. And once again, here, the SST is the key, is the answer for proper distributed resources management. For example, here you can see one SST, which is really similar to STAR's SST, made by Thirte, that has already been installed in a microgrid with medium voltage storage in the context of Tygon, which is a Horizon 2020 project. Now the question is, how does the STAR project contribute in storage system integration in the medium voltage grids? So apart from designing and manufacturing the SST, the STAR project also has one task, which was led by CERT. It is about the combination of solid-state transformers connected to the power system coupled with storage. Okay, so in figure 6 here, you can see 4 SSTs in series connected to the power grid in MATLAB. On the other side, we have storage systems, 1 per SST. And here you can see even more close a dual active bridge circuit with the high frequency transformer. And then we have some of the results. So simulation results. In charging mode in figure 8, you can see the SST module performance when charging. You can see the age bridge AC voltage. You can see the DC voltage of the capacitor. You can see the voltage reference and the voltage angle. And here you can see it zoomed. And finally, we have the discharging mode. We have the same quantities, but the other way around. We have the discharging DC voltage, the discharging angles, and so on. And here you can see it zoomed as well. And of course, I fully understand that these are merely simulations, but still they highlight how promising this SST technology of the STAR project will be. Okay. So thank you for your attention. I hope I was brief. I hope I was kind of interesting. Do you have any questions?
Thanks, Maria. In fact, we are now starting with the Q&A session. So if you have some question now, it's time to write it down in the dedicated chat. So let's see if we get something. Okay, I have a first question. What has been the main challenge you've encountered so far in this project? So I think that it would be nice to have one reply from iPLUG and one from STAR. So who wants to say something?
Well, perhaps I can say something myself also as a coordinator of iPLUG, and it's also kind of related to the conclusions perhaps of the discussions. In our case, the main challenge, in my opinion, and also perhaps my colleagues can say something later, perhaps it's related that we are doing research in different topics at the same time, right? We are developing a converter for low voltage and medium voltage, and we are doing research on the power electronics. And at the same time that we are doing the research as well on the planning, let's say, the sizing, the location of these converters in a grid. And then normally to do that, then you need to take into account the cost of the converter to see how much you are saving, and if there is a real benefit in installing this converter in a specific application. And this also requires some research work, but also somehow we until we have final results from the power electronics development, it is hard to quantify exactly what it is the cost of the converter we will install, right? And the colleagues cannot tell us in detail about that. So this makes it, I would say it is a challenge on the global outcomes of the project. But I think in this kind of project at low TRL, it is okay. But I think it is something good to acknowledge and to, in my opinion, to highlight as the main challenge, right? We are advancing the technology in the different work packages, but it is not as straightforward to give an integrated solution of the whole project that will have an impact, let's say, because it depends on the success of the different research we are doing in the different work packages, which is not finished yet, right? It requires further work. Okay, this is, well, my point of view on this question.
Thanks, Oriol. I asked Jonathan, since he is also coordinating, or Eduardo, as you prefer.
Yeah, I will say, or Jonathan, you want?
No. I think that we have faced several challenges, especially technical ones for sure. But I think one of the main challenges that we have faced is that we have to fix is one of the isolation design, the design for keeping the isolation to the objective of the STAR project based on medium and high voltage. That's one of the main challenges that we have faced from the initial point of the project, and we had to work really hard with the rest of the consortium and the contributors in order to finally design an APT with all the technical specification in order to fulfill the initial objectives. I don't know, you have to add something, Eduardo, from a
Yeah,
more technical point of
the,
view.
the
I don't know.
the design of the IPT after the summer, the IPT will be tested at 300 kilovolt lighting impulse, and it is very challenging. It is designed to handle this, but of course there will arise some information regarding the design of this isolation that is very challenging for this medium frequency transformer.
Okay, thanks. And strictly connected to this question, there is another one that is interested. Have you already identified any potential follow-up or future developments? Since we are always discussing about exploitation of the results we are trying to achieve. So have you already, I know that the projects are still running, but some time has passed since the beginning. So have you already identified some potential developments? I will put again the question maybe to Oriol and Jonathan, as you have the main picture of your project, and maybe you can answer to these questions. But the other can intervene, of course, if they have something to add. Yes, Maria.
Well,
sorry, Oriol. I saw Maria raising a hand.
No. It's perfect that Maria starts. Yeah.
Okay.
Thank you. Well, I think, as I said in my presentation, the exploitation would be like towards microgrids and energy communities. Something like this, something that requires a more advanced control.
Okay. Oriol, from your perspective?
Yeah. Also from our side, we see these are relevant applications. We have done some, let's say, exercises on trying to see the business cases where these solutions could make sense. And I agree with Maria that yes, microgrids in general, energy communities can be good applications. Also for us, we were looking at also some additional like EV charging stations or things like that, which could be part of what Maria was suggesting, but well, related to it. And well, apart from the generic possible applications, also we have started to contact some companies who could be interested, but well, for now it's not there is nothing sure about the continuation of this, but well, we think it's important to continue and to find some use cases, but perhaps in our case now we should we should arrive, let's say, to the field, let's say, and bring this to a real application. This project was more research. Now it's time to perhaps work with some companies integrating the solutions and go to a pilot or something like that. Yeah, this is what we see as the next step, but we are working on that.
Yeah, I understand. It's a sensitive part that has to be managed, because of course we are developing something commercial that could become valuable for companies working in the field. So the last questions, and I put it on the table for all of you. You already answered partially. So if you have already received any interest or engagement from external stakeholders, someone that, as you said, Oriol, already started some discussions with you related to the technology, or if you are planning to address, I don't know, maybe association or organization representing a special kind of targets that could help you reaching the target in a more efficient way. So if you have done already something with this kind of subjects.
Should I ask? Should I start? Well, in our case, yes, continuing what I was saying, yes, we have made some initial contacts. actually it's part of one of the work packages now that we have some tasks to do, and one of them is to talk to some associations and try to promote further the concept and go to higher TRLs. So yes, I could say we are working on this, and we hope to to find some interested parties for continuing with the project. In our consortium, we had one small distribution company, which could be one possibility. They are already involved. But well, also the concept we are developing, in our case, it's perhaps not applicable. It's not something we think that it will be installed in all the distribution feeders. It's something that it can be useful in specific applications. So also we need to find let's say the partners with the right problems and willing to acknowledge that they have this problem and to work with us to improve in that sense. So yeah, it's not easy, but well, we are confident that we can do that. Yeah. Mhm.
Great, thanks. Jonathan, do you want to, or Angela, if you want to add something?
Yeah, I would like only to add that interest towards biodegradable dielectric fluids is growing because of their clear advantages, and I'm thinking that it's important to stress the strong connection that could be between this kind of technologies and biodegradable fluids, because I suppose that this technology will be installed near how can I say, houses, people, and so safety aspect is an environmental aspect become pivotal for the for this kind of structure. So we'll be happy to see how it goes and to collaborate if something new comes up.
Thanks, Angela. I agree, since even if we are talking about something very sectorial and addressed to companies, the safety issue and the circular and environmental friendly process, it's something really important. It's something that the Commission is asking, and it's the combination of these two elements, I think, represent an added value for the solution. Okay, I don't see any further questions. If there are some more, otherwise I would just leave the last remaining minutes to Oriol and Jonathan to make the closure of this webinar. So I don't know who of you want to start first.
Really, if you don't mind, you have been talking first, so I can start, and then you can close with your conclusions if you want to. Okay.
Yeah.
Okay. Yeah, I will be brief. First, I would like to thank Icons first for organizing this webinar, and iPLUG project for accepting sharing this space with our project SSTAR. Thank you all attendees and panelists for such an insightful and dynamic session. During this workshop, we have explored critical advancements, positioning power electronics as a cornerstone of future distribution, okay, and advancement positioning power electronics and transmission networks, okay. So for example, from our colleagues from iPLUG, contribution is planning and control of multiport converters. From SSTAR's side, we are working on innovation in bio-based dielectric insulation, high voltage IPT design, and decentralized control strategies for solid state transformers. We have a lot of key challenges ahead, and we are trying to escalate and to fix, such as scalability. We have been talking about electromagnetic compatibility, thermal reliability as well. But also, I would like to emphasize the strong potential for collaboration to drive this solution toward higher TNLs and market orientation. You were talking about the future deployments and developments of these kind of technologies. We are For instance, in SSTAR project, we are working in TRL4. So we will try to fix some of these kind of issues that we initially identified, not only in the market but also in the literature. This kind of gaps, cover this kind of technical gaps that we currently have. Okay. So we will try to fix it and to scale up this kind of TLS in order to improve this kind of solutions, technical solutions. Today we have again confirmed that innovation in power electronics is not just a technical ambition, is a necessary part toward building a more resilient and sustainable energy grid. That we have seen several slides in your presentation in terms of this crucial link to the sustainable world. Okay. So yeah, that's all from my side. I invite all of you to keep informed about the progress of both projects. And again, many thanks for joining this workshop. And we will keep working and running on this topic. Okay.
Thanks, Jonathan. Mario, do you want to share some
Yes.
final thoughts?
Yeah, sure. Well, also, yeah, following Jonathan's acknowledgement, let's say I also would like to thank you for Icons for organizing the webinar, and also the colleagues of SSTAR for the good work they are doing. It was shown in the presentations, and well, it's very interesting also for us to learn about their work, and of course also thank you our contributors from iPLUG as well for their presentations. And yes, well, also in our case we are working in the project. We are trying to advance, let's say, on the different technologies. Also, now that we are in the last months of the project, we are also thinking about how to continue working in all these topics. But well, we think that, well, we have learned in the project. We think that we have developed interesting work, but also there is a lot to be done in the near future. We see important potential in distribution networks for the integration of power electronics, and yes, well, the idea is to keep working in all that. And then perhaps regarding also this collaboration, yeah, I think it's good to keep this link between the two projects. Perhaps also after, whenever we finish, we can keep discussing about further collaboration. Yeah, and well, thank you everybody for the interesting webinar, and yeah, I think nothing else to say from my side. Yeah, thank you very much.
Thanks. I also would like to thank all of you for joining the webinar, the participants and the speakers, and we will surely move on with the collaboration. In the meantime, I remind you to follow both projects on social media and on the websites. You can find all the news updates, information about what's going on, and you can keep a link to what is moving forward. You will receive an invitation for a further initiative that we will launch. So stay tuned. And thank again everybody. And I don't know, Erika, if we have to leave some closure remarks, or if we can just close the webinar and greet everyone.
I think we can close and greet everyone.
Okay, great. Thanks a lot. So
Thank you.
Thank you.
bye.
Thank you. Bye-bye.
Thank you.
Bye.
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 Thank you. Bye.